This is an AQA A-level chemistry question based around the topic of organic synthesis with also some amount of substance as well. So try each section, pausing as you go, and then review your answers at the end. Here's part A, part B, part C, parts D and E, and finally part F, taking you to a total of 20 marks. So for part A, we want the IUPAC name for compound F. Well, we're going to look for the longest carbon chain, and we want the carbon chain that has got the carboxylic acid in. So I've highlighted that in green, and you can see that we've got two methyl groups coming off in the second and third position. So they give us the start of the name. They act as the prefixes. We've got 2,3-dimethyl. And then we have got butane dioic acid. Now, two carboxylic acids means we do go to dioic acid, but really, really crucial here is the magic E. This E that has to go in the name to be credited with the mark. Butandioic acid would not get you it. Okay, we move on to part B. Deduce the structure of compound D. For each of the conversions in step 1 and 2, suggest a reagent for the conversion and name the mechanism. So you are looking here at a series of steps to get from C to D to E to F. And we're looking at, in D, something that we can make from an alkene and something that we can convert into a nitrile mechanistically. And the one thing that falls into that category is a haloalkane. We can make haloalkanes from alkenes and we can turn them into nitriles, and we can show that through different mechanisms. How do we do this one? Well, to do it, we would add HBr. And in adding HBr, you'll notice that we are gaining a Br on both of the double bonds, and we're adding an H on both of the double bonds. The mechanism itself is electrophilic addition. The electrophiles are attracted to the electron-rich double bond, and it's addition because we start with a double bond and then we lose it because we add things on each side. When we move on to step 2 and how we convert haloalkanes into nitriles, or in this case a dihaloalkane to a dinitrile, well, that one we would use KCN, could have said NaCN, and the mechanism is nucleophilic substitution, where the CN- attacks the delta positive carbon, causing the Br to be lost. So if you've got your basic knowledge of these mechanisms, you can apply that. The only real difference that we have here is we've got the same mechanism happening twice within the species. And that's true for the electrophilic addition and the nucleophilic substitution. What's the type of reaction in step 3? Well, step 3, we're going from nitrile to carboxylic acid. The type of mechanism we're looking for there is hydrolysis. Moving on, we've got part C, where we have got F and G labelled. And your job is to state a reagent or combination of reagents that can be used in test tube reactions to distinguish between them. Describe what you would observe when the reagent is added to each compound and the test tube is shaken. So there's more than one answer here. I'm going to look at one or two of them. Ideally, I'm going to recommend that you look for the different functional groups, and we can see that F is a carboxylic acid and G is an alcohol. It's actually a primary alcohol. Now, for that reason, we might go for acidified potassium dichromate 6. And with F, we would get no visible change. We cannot oxidize a carboxylic acid, but we can take a primary alcohol and we can oxidize it. And it could come to an aldehyde, and it could go on to a carboxylic acid under reflux. So for the F, there would be no visible change, but in G, there would be a colour change. It would go from orange to green. But alternatively, you might want to prove that the acid is the acid. And to do that, you could add any metal or any metal carbonate. And when you add a metal or a metal carbonate to a carboxylic acid, it will form a salt, it will form a hydrogen, and because it forms a hydrogen, it will effervesce. In this case, the alcohol, there will be no visible change. Moving on to part D, we have compounds F and G reacting to form a polymer. Draw the repeating unit of the polymer. Now, we're dealing with a condensation polymer here, and if you have a look, I've highlighted where the water is going to be lost. So we take the OH off the acid and the H off the alcohol, and once you've actually done that and you can visualise very, very clearly what the species is going to look like, you can get to the final structure. You can see here that the CO, this CO here, connects to the O. There's the O here. And we take that right the way through until we get to our repeating unit. And that O would then join with another over here. And for part E, we have a little bit of a calculation now. In an experiment, 0.93 kilograms of purified F were obtained from 1.11 dm cubed of G, and its density is 1.04 grams per centimetre cubed. We want the percentage yield. So in the first instance, I'm going to work out the mass. I've got mass is density times volume. My density is 1.04 grams per centimetre cubed. I was given my volume in decimeters cubed, so I need to multiply that by 1,000 to get to centimetres cubed. And I get 1154 grams. Now, I can then work out the number of moles of G. And I do that by taking my mass and dividing by the MR. You can calculate the MR, you add up the relative atomic masses. I'm going to leave you to do that for yourselves to confirm that it comes to 118. So 9.78 moles. Now, on a 1-to-1 ratio, we would expect then 9.78 moles of F. And if we know the moles we would expect, and we know it's MR, and we can calculate that as 146, we know that we would theoretically expect a mass of 1,428. But we didn't get 1,428. We got 930. So the final part of this is very, very simply, what is the percentage of 930 out of 1,428, and it gives us a percentage yield of 65.1%. Finally, moving on to F, one reason for a yield of less than 100% is that G reacts to form a number of other compounds. The other compounds are all liquids at room temperature. What technique could we use to separate and collect each of these compounds? Include a description of the apparatus. The description could be a labelled sketch, it could be a description in words. So what you've got to do here is apply your knowledge of how we've previously separated liquids. And the way we do that is fractional distillation. In terms of the apparatus, I've added on here what you might be looking for. You would need all of the key components, and I'm going to highlight what those key components are, either to show on the diagram or to do in writing. And you can see that we need apparatus for the fractional distillation must clearly work with the fractionating column. That's things like having an opening going through, not having a line going across as if it's sealing it up. Cross-sectional all the way. You must include the fractionating column, you must include the thermometer, you must include the condenser and the water jacket. And if you do all of that, you get to a suitable diagram. That takes us to the end of this question. Thank you for listening.